And let me go ahead and pop this open. Alrighty, let's go ahead and get started today. How exciting. Okay, here we go. We're going to be talking about numbers in science today, or chemistry for us. This is chapter 2A for the textbook that we're going to get through, and we'll probably start 2B today, depending. We'll see how far we get. We're going to basically be covering how we talk about numbers in science, because it's a little bit different than numbers in math or just numbers in real life, because in science we're going to be dealing with really, really big or really, really small quantities that we may not be able to communicate as effectively as we would be able to say, like, hey, it's, $3.29 for gas, something like easy numbers like that. In science, we often have harder numbers to deal with. Good morning, Dominique. So we'll deal with those. Just so you know, I just put in Discord for you guys. Where did I put it? Let's see. I put it in the handouts tab. There is a little chart there that has some metric stuff that you're going to want to learn. So go ahead and look at that later. You're going to basically want to learn all the information on that, from everything between giga to nano down there on this chart. So we're going to be learning the prefixes starting probably tomorrow, but the faster that you get on those, the easier it's going to be. So that's on Discord for you. Honestly, you can just Google metric prefixes, and I'll just write this right now. Yeah, hint. Start learning metric prefixes. And then for us, that's between giga to nano. Those are the ones we're going to focus on this time. So yeah, that'll be exciting. So that's in Discord, or again, you can just Google them. You're going to find tons of charts like this where you can just, learn it that way. So we'll actually start working with those tomorrow, but yeah, we'll get going with that. So cool. Let's go ahead and get started then. Of course, if anybody has any questions from last time, any of the stuff we talked about with energy or separation of matter or whatever, always throw those out there. I'm happy to answer them. But yeah, your first homework stuff I think is going to be due this weekend. You're going to have some stuff on some of this math that we're going to be doing. So in science, we use big and small numbers frequently. For example, we can say your body has, I don't know, I'm just going to make this number up. That many cells in a human body. That's 11,289,000,000,000, blah, 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 blah. Good morning, Becca. Okay, again, I'm making this number up. It's somewhere in this range, trillions, but big number, right? Or we can say an atom weighs something like that, grams, where the zeros just keep on going. So we often deal with very, very big or very, very small numbers. And so we tend to make them easier for us by transforming them into exponential functions instead. So instead of talking about these crazy big numbers, we use scientific notation. And generally that's going to be good morning. Scientific notation is going to be generally used for numbers that are, I don't know, bigger than 1,000 and smaller than 1,000th. That's generally where we're going to be using it more often, but you'll see some people will use it for everything. So, but for us, it's generally things that are bigger than 1,000 or smaller than 0.001. So how scientific notation is going to work is we're going to have some number in here between 1 through 9. Then we're going to have a decimal point, and then whatever else we need, times 10 to the, I'll just put a blank there, not a question mark. So we're going to have whatever we need here. And we're going to have some number for our power of 10. For example, if we had the number 1024, we could move this into scientific notation. How we want to do this is we can only have one number in that pre-decimal spot. And it has to be a number between 1 and 9, inclusive. So you can have 1 or 9 there. And so if we want to do this, I'll just show you what it is, and then we'll talk about how we get there. So we could say that this number would be the same as writing it this way, where we will transform it into a number that has one number before the decimal point, as many afterwards as we need, and then we're going to have an exponential function to tell us kind of how big or how small it is. Hopefully in your math, algebra, or whatever class that you learn this sort of thing in, this should not be terribly new, hopefully. How we get this is if we look at where the decimal would be in our number that's on the left there, the 1024, that's going to be over here, right? If we were to put a decimal in this number. And we would essentially be moving that decimal such that we have just one number next to it. And so we can see we're going to move it once, twice, 3 times in order to get it in that nice spot where we're going to have one number to the left of it. And as a result, since we moved the decimal 3 times, that's where this number comes from up there. Because we moved the decimal 3 times, in this case we moved it to the left, we're going to get positive 3 as our exponent there. If we had this number instead, I can go ahead and convert that to scientific notation as well. But we're going to see we're going to have to move the decimal the other direction. And as a result, our exponent will be negative. So if you see here, we're going to move it again 3 times so that it ends up where we have one number on the left of the of the decimal point, I'm sorry. So you see we move the decimal point 3 times. In this case, it was to the right. And so this left and right thing can be somewhat confusing at times, but it may be easier to just understand that if you have a positive exponent, that's going to be a large number. Something greater than 1. And if yours is negative, that means a very small number. So here, I'll move that up a little bit so you can see that. So hopefully none of this should be necessarily new, but we're still going to kind of just go over it again just in case, or maybe it's been a while since you've done math with exponents. So we can go ahead and do a few. Why not? How about we do the number... Let's go ahead and put both of these into scientific notation. We're going to be talking about what to do with all these pesky zeros in a little bit. For now, let's just not worry about them. But we're going to talk about that later today, and you'll hate that. But we'll do it anyway. So if we kind of imagine where the decimal would be in this first number, the second number we know where the decimal is, right? We can see it. It's written out there explicitly. Yeah, exactly. Exactly. That's what we're... Oh my gosh. Oz, relax. Come here, buddy. Come up here. Relax. Right. So we're going to want to move it 5 times. 3, 4, 5. And exactly we get 3.23 times 10 to the 5th. Perfect. And then exactly we're going to want to now move... For the second problem, 1, 2, 3, 4, 5, 6. So that tells us we have 4.62 times 10 to the negative 6. Remember, if you're moving your decimal for a small number, it's going to be a negative exponent. If it's a big number, it's going to be a positive exponent. You can think about it in terms of left and right, whatever works for you. That's how you would do it. But for us... I just like to think of it big number, small number, so easy enough. The reason I try to avoid left and right is because when you're going from scientific notation back to regular notation, that's when the left and right can get confusing. So if we take, for example, something like this, and put it into regular notation. In order to get a negative exponent, we move our decimal to the right. So if we have a negative exponent and we want to make it kind of turn back into a regular number, we would have to do the opposite. So this time we're going to have to go left. That's why I don't like this left and right, because it's troublesome that way. But we can see right now this number should be less than 1 because it has a negative exponent. So we're going to have to move our decimal place twice. So it's now going to be over here, which tells us that this number is 0.0. That's what that first one should be. We're going to have to put a 0 here. 201. Yep, exactly. And if we had something big, we can do that instead. I don't know, how about 9.942 times 10 to the, I don't know, 8th. We're going to have to move our decimal now accordingly 8 times. So I'm just going to, let's see here. So that's 3 times 4, 5, 6, 7, 8. We just need a few zeros there to account for that. So hopefully none of this is terribly new, but if this is troublesome to you, go ahead and just like Google scientific notation for Khan Academy or something, and you'll have plenty of problems to work on there if you want to kind of practice that. Cool. But for us, that's as far as we're going to go with kind of practicing in class for that. So awesome. So again, this is just a way for us to be able to easily communicate really big or really small numbers to each other that don't have to deal with 30 zeros and thinking, oh my god, how many is this? And just easier that way. Just so we remember, actually let's talk about multiplication and division in a little bit. We're going to talk about right now the dreaded Sig Figs. So in order to do that, we have to talk about measurements a little bit first. most of the quantities that we deal with in chemistry or in science in general are measured. Some way, somehow they're being measured. So either that's a volume measurement, we know how many milliliters or something we have, or if it's a mass measurement, we know how many grams we have, or, whatever. These sorts of things, we rely heavily on measurements I'll write it. So, Khan Academy. So just Google Khan Academy and then scientific notation. And you can practice some more of those there. There's also some just like kind of general like algebra and stuff review that you may find useful as well. And it's all free, of course, and exciting. Yep, no problem. So in chemistry or science in general, we're going to see that we have to do a lot of measurements. And so a lot of the numbers that we're going to be working with will come from these measurements. And so I will present you with the classic example of the lovely ruler. And we're going to take, I usually use a leaf, because why not? I like drawing leaves. Here's my lovely leaf that looks suspiciously like a football. If we wanted to measure the length of this leaf, for whatever reason, you would align it with your ruler and you'd try and measure, okay, how long is it from, tip to tip. And we can see here that we know the leaf is between we know for sure, 100% for sure, that it is between 1 centimeter and 2 centimeters. However, we don't know exactly where it is, right? We know it's between those, and we're going to be able to kind of make an estimate of where this is between those two. As we can see here, maybe, I don't know, if I were to make a guess, I would say this is probably 2.7 centimeters. So not quite, I'm sorry, not 2.7. I don't know how to do numbers apparently. 1.7. We know it's between 1 and 2. That much we know for sure. And looking at this, I say, okay, it's closer to the 2. And so maybe it's 1.7. Maybe you might say it's 1.6. Or maybe you're reading this and you see it as 1.8. Somewhere around there. What's interesting about this is that technically all three of these are right. Technically, one of them would be better than the others, but because these are kind of estimations, it depends on your eyes, right? And so just how you like to view things. Notice, though, that all of these have the same digit before the decimal point in this case. Because we know with 100% certainty that it is bigger than 1 centimeter and smaller than 2 centimeters. So we know that this, the number on the left there should be 1. We know it's greater than 1, but less than 2. However, how about purple? Too many colors. This last number is uncertain. We don't know if it's 0.7 or 0.6 or 0.8. We know it's somewhere around there, but we're not certain about it. We can't say, yeah, this is absolutely 1.7, no doubt about it. There's definitely some doubt there. It could be 1.6, it could be 1.8, somewhere in there. So it's understood that in science, what other colors do I have? Light blue, why not? We know that measurements, let's see, how do I spell measurements? There we go. they will always carry uncertainty in their last digit. We're going to do the same thing again with a better ruler, and we're going to see that we're going to get more information out of that better ruler. All right, so let's go ahead, and I'm just going to copy this because I can cheat that way. I don't have to redraw my lovely leaf. Here, I'll just hover over here for a sec, in case you're writing or whatever. So it's always understood that your last digit in whatever you're measuring is going to be uncertain, just because it depends on how good your measurement device is. You know, obviously, like a scale that would be used to measure the mass of like a giraffe. You have the secret lab chair. Awesome. Omega? I'm pretty short, so I have to have the Omega, I guess. But I like it because it's blue. I like blue. A scale to like measure the weight of a giraffe versus the weight of an ant obviously would have to have different kind of accuracies, right? You'd want your giraffe one to be able to measure really, really big masses, and you'd want your ant measuring one to measure really, really small masses. And so, you know, it doesn't really matter if the giraffe is, you know, 4,652.2221 pounds. Like, that last decimal point, who cares, right? That's going to be changing, you know, second by second as the giraffe, you know, breathes, basically. But for an ant or something, those really small numbers become important. And so let's see what this looks like. So I'm going to go ahead and try and draw here. Okay, I've already failed, but that's okay. Here, let's try that again. Okay, I'm going to draw my half mark first. There we go, that's kind of better. All right. So with my lovely drawings now, maybe we can see a little bit better. So what do these little little marks mean? Those are going to be intervals of 0.1 centimeters, right? We can see that there are 10 of them in between 1 centimeter and 2 centimeters, so that's going to be the 0.1 centimeters, or 0.2 or 0.3, whatever they are. And so if we go ahead and like kind of, didn't that zoom it? Oh, there we go. If we zoom in on this, aha, this one here, that's got to be 0.5, right? Here, let me make my thing a little bit smaller. That's 0.5. I'm sorry, that's 1.5. My bad. And that one is 1.6 right there. It's hard to draw on this super zoomed in one. Hopefully we can tell that, though. I mean, we know how to use a ruler. So we can see, okay, yeah, that leaf is now for sure in between 1.5 and 1.6. So let's zoom back out to normal here. Switch back to normal pen width. I think I did this in dark blue. Yeah. Okay, now we know for sure that the leaf is more than 1.5 centimeters, but less than 1.6 centimeters. So we know it's somewhere in there. And so, if we want to try and make this guess, what do we think? What do we think this one's going to be? 1.58, 1.59 or something? Definitely closer to the 1.6 side of things, right? So again, we're going to kind of make our last digit bigger. So maybe it's 1.57, 1.58, 1.59, somewhere in there. go back to roughly 100%. So maybe perhaps it is 1.58 centimeters. Just again, understanding that I'm using my best kind of guesstimate here with that last digit. So again, this time, what colors did I use? I don't even remember. These ones we know for sure. This one is going to be the uncertain one. So just like before, we're going to have some that we know absolutely for sure. There's no doubt about it. But the last one is kind of a guesstimate. So we're going to see here that, again, it's that last digit. It's always going to carry that bit of uncertainty. And so if we were to take the numbers, last time we guessed maybe 1.6 or 1.7. Let's say 1.6. We're going to see that this one will be the better measurement. And the reason for that is because it came from a more precise instrument. In this case, that's a ruler. So we had a better ruler, so we're going to get a better measurement. So the kind of the more money that you spend on your fancy rulers that have all these fancy little tick marks and graduations. How do I get rid of this? Let's see. Let's go to 100%, and hopefully that'll get rid of these silly things on the side. Kind of. Okay, we tried. The more kind of like the better your ruler is, the better your measurement is going to be. The more accurate it's going to be. So as a result, the same thing kind of happens with all the other measurements. If you want to have a scale that can read, 0.00001 grams or something really small, you're going to end up paying a lot of money for it. For example, those often cost, like $10,000 to get a scale that can measure that small. Versus if you go to, Walmart or whatever, you pick up a bathroom scale that can measure, if you're looking at grams, it's probably not even 1 gram or something. You're probably measuring the tens of grams or pounds or whatever. Those are going to be cheaper, right? You can pick one up for $20. Often the more precise instruments, whatever you're using to make your measurements, are going to be more expensive versus the ones that give less information. And that kind of makes sense, right? You're putting more effort into making one that can make better measurements. So we're going to see here that the kind of number of digits we have in a number, that's nice and numbers about numbers. Number. No, we can try that again. Number. Depends on our instrument. And simply put, more digits is a better measurement. All right, let's see. Can you be quiet if you go on the couch, perhaps? Let's see. All right, does that kind of make sense? So the more money you're spending on your instrument to measure stuff, Oz, shush. Relax, buddy. The better measurement you're going to get out of it. And so this is where we're going to start learning about Sig Figs. Figures. We're going to see that this is something that's going to be very important for us because it's going to be able to tell us no matter what we're doing, how good our measurements were. these tell us exactly how good your measurements are. These tell exactly how good your measurements are going to be. So if we look at the numbers 1.6 versus 1.58, those were the numbers we got for our leaf or whatever it was. We're going to see that this one is going to have 2 significant figures, whereas this one will have 3 significant figures. And so the more sig figs you have, the better your measurement was. And like we saw that again here, right? We see that we have more information with the second case. We saw where that 1.5, 1.6 was, so we could make a better estimate. And so we're going to see the more sig figs you have, the better your measurement is going to be. All right. So now we're going to focus on how to count sig figs, significant figures. There's going to be 4 rules that we're going to deal with. 3 of them will be kind of no problem, and the last one will be the tricky one. So our first rule, our easiest rule, is going to be any non-zero digit is significant. So anything that has a number with it will be a significant digit. So if we, I don't know, let's take some numbers. Oh, shush, little one. If we look at these just 2 random numbers that I have, this one will have 4 sig figs. This one will have 3 sig figs. It's telling us that all of these numbers are significant. And so we would count them. We would say, okay, this number on the left has 4 significant figures. The one on the right has 3 significant figures. Easy. Not too bad, right? Oh, that's creature down there. The next rule tells us that leading zeros, which we'll talk about what those are never significant. So if we take the number, if we take James Bond's number, 007, or we take the number, let's not put a 0 there. Yeah, there we go. We would see that this number on the left just has 1 significant figure. The zeros that are in the front of a number, which we call leading zeros, are never significant. So normally if you say, you know, I have 7 bananas or whatever, you don't say I have 007 bananas. Like, why? You know, there's really no point at all. And so you can already tell that putting zeros there does not alter the significance of your measurement at all. And so, as nobody would typically say 007, I have 007 bananas, I have 010, 7 bananas. Like, it's just way more work. You know, you don't need it. So those don't count. It's going to be the same case if you have a decimal point. We're going to see that this number is going to just have 3 significant figures. The reason for all of this is if we were to convert that number to scientific notation, we would get rid of those pesky leading zeros. And we're going to see again here that we're going to have still our 3 sig figs there. Important to note, these exponents don't count. They do not have sig figs, so you do not have to worry about the exponents for when we're looking at sig figs. And so we're going to see that putting things in scientific notation is going to help later on because it's just going to get rid of all these pesky zeros that we don't need. But we'll look at that in just a little bit. All right. So non-zeros, always significant. Leading zeros, never significant. If we look at the third one here, is that zeros in between numbers 1 through 9, non-zeros, are always significant. Oh, I'm gonna run out of room. All right, let's write it down here. So anything in between a number, 104, we can see here that we have a zero in between a non-zero. In between non-zeros. And so this number will have significance on that zero. If we throw more zeros in, all of those are still going to be significant. So anytime we see zeros in between whole numbers, that's when we're going to have them be significant. Let's throw things a little bit more here. So let's look at this one step by step. First thing is we can identify that all non-zero numbers are significant. So let's just go ahead and underline those. So we know those for sure are significant zero or significant digits. We now have 3 zeros to deal with. If we look at the zeros on the left, those are going to be leading zeros, right? Yeah, exactly, Becca. So those leading zeros do not count for sig figs, but that zero in between the 2 and the 6 does count. And so overall, this number will have 4 significant figures. So it's going to put some X's on top there. Those are our leading. So leading zeros do not count for sig figs. And again, if we were to put this number, or if we were to put all of these numbers into scientific notation, we would be able to see exactly how many sig figs are going to be there. We're going to see that scientific notation will always give us only sig figs. It will only give us sig figs. So if you can put something into scientific notation, everything is significant. Easy. You win. So then you don't have to worry about stuff anymore. Okay? So far, so good. We'll have plenty of practice with this. Here comes the 4th rule. So, we have talked about non-zeros. We've talked about zeros before a number. We have talked about zeros in the middle of a number. And so the last case, of course, is going to be zeros after a number, which we call trailing zeros. And these are going to have a conditional placed upon them. They will sometimes be significant, and that's why they're the tricky ones. So they will be significant. I'm going to put this in big purple. Why not? If there is a decimal point. Oh God, that's really ugly. number. All right, so big purple, very important here. Trailing zeros will be significant if there is a decimal in your number. Anywhere. If your decimal is anywhere in the number, those zeros will count. So let's look at some examples here. All right, here's a bunch of numbers. So we're looking at, with the trailing zeros, we're looking at if there's a decimal point somewhere. So if we look at the first one, of course we know that 1 is going to be significant. That's a non-zero. We have trailing zeros now, so we have to ask ourselves, is there a decimal point in this number? And yes, I see a decimal point. It's, right there, 10.0. So these will count. So we will have 3 significant figures for that first number. If we look at the second number, however, of course that 1 will be significant. However, I do not see a decimal point in the second number. And because of that, that 0 will not be significant. So we will only have 1 sig fig for this number. If we look at the next number, creature relax, buddy, we're going to have, again, 1 significant figure because we do not have a decimal point. So those trailing zeros will not be significant. And if we look at the last number, of course, we have at least 3 sig figs there. We have a couple of zeros to deal with. If we look at those first 3 zeros, those are in between. Zeros in between, yes, those count. So those will count. And we do have a 0 at the end. So we have to look, do we have a decimal point somewhere in this number? We do. And so that 0 will count. And so overall, 1, 2, 3, 7 sig figs. Will be how many that number has. We'll do a few more in a second here. But I want to illustrate a point. Notice that these numbers in the middle, the two of them, 10 and 1,000, they both have the same significance, but they're very different numbers, right? Would you rather have $10 or $1,000? There's obviously a difference. You would choose 1,000, right? 1,000 is definitely a bigger number. So significance doesn't really tell us anything about the kind of like magnitude of the number. It just tells us how good your measurement was. So zeros can be important even if they're not significant because they need to be able to tell us how big or how small a number is. So those are called placeholder zeros. Let's do that in green. Oh, let me not underline them. All these zeros there are important because they are telling us how big the number is. However, they are not significant digits. How do we know this? If we were to convert these numbers into scientific notation, we would have 1 times 10 to the 1. And this number would be 1 times 10 to the 3rd. Notice that even though the base number there is still the same, the 1, these are going to be very different, right? So that's where those kind of placeholder zeros go. So that's going to tell us again the magnitude. So placeholder zeros will kind of tell us magnitude. That's what I'm trying to say. Magnitude meaning how big or small the number is. So that's where those placeholder zeros are going to go. All right. Let's do some practice because I know this can be confusing, all this zeros nonsense that we're going to go over. Using always the same numbers, aren't I? Okay. Apparently I am liking the number 4, which has shown up in all of these numbers. It's so hard to just come up with numbers on the spot, you know. You always are like, okay, let's make them different but the same. Okay, let's look at these. So, whenever we're looking at how many sig figs, or let's just write that. How many sig figs do these numbers have? So, let's go ahead and take a look. With this first example, we can always start by knowing that our non-zeros are significant. So we know that this number has at least 2 sig figs. Then we want to kind of go rule by rule, maybe. Do we have any leading zeros here? Yeah, we do, right? We have 2 leading zeros, so we know we're not going to worry about those. We do not ever worry about leading zeros. So we do not count those. Next, we want to look, do we have any zeros in between? Nope. So moving on, do we have any zeros that are trailing at the end? Yes, we do, right? And so we have to look, is there a decimal in this number? I see a decimal point. If you have a decimal point, that means yes, it is significant. So we are going to have that last zero there be significant. So this number will have 3 significant figures. Is that okay? When you're kind of starting out with this, you probably will take some time looking at them for sure. But you're going to see that this will become second nature pretty soon. Maybe only like 3 cries in the shower, and you'll be good. Though actually the real pain is when we start using sig figs in numbers, but we'll get there. All right, looking at the next number, non-zeros. Let's go ahead and just get those out of the way. Do we have any leading zeros here? No leading zeros. Nothing in front, right? Do we have zeros in between? I see a 0 in between the 4 and the 1, so that's going to count. Remember, zeros in between are good. They are significant. And then we have a 0 at the end. Do we have a decimal point in the number? No decimal point. So this number will have 4 significant figures. I'm going to just put the red one on top to say it's not significant, because we have no decimal. No decimal, so it's not significant. All right. Next number, 2, 9, and 4, we can check. Do we have any leading zeros? Nothing in front, so nope. Do we have any zeros in between? We do. Zeros in between are yes. We have nothing else. We have already figured out that this is, everything is significant there. Okay, cool. Moving on then. Looks like we have a 4. Do we have leading zeros in this case? We do. Remember, leading zeros do not ever count for us, so we're not going to worry about those. Do we have trailing zeros? Or, sorry, do we have zeros in between? We do not. And we're going to see we have trailing ones as well. And we do not have a decimal. So this number will only have one significant figure. All right, so because there's no decimal point there, we will only have one sig fig. Alrighty. Next number, we have non-zero. Do we have leading zeros? We do. Remember, leading zeros don't count. Never count those. Do we have zeros in between? Nope. Do we have trailing zeros? Yes, we do. Do we have a decimal? We do. So those will count because we have that decimal. So this will have 3 significant figures overall. All right, and if we look at our last one here, we have a bunch of non-zeros. Do we have trailing or leading zeros? No. Do we have zeros in between? Also no. Do we have zeros at the end? This time we do, yes. Do we have a decimal point somewhere? We do. It's right after the 8 there. So those will count. All your trailing zeros will be significant. And so overall we're going to have, looks like 7 sig figs there. Any questions on any of those? So this is stuff that probably just takes a little practice, getting used to. There is a homework assignment on it that you'll be able to do. And the way that the worksheet is kind of designed is that it kind of teaches you the rules as you go through it. So you'll see how that's going to work. I think it's called Measurements in Sig Figs. So you'll see how that's going to work. You're welcome to go ahead and start that. It is going to contain some stuff that we're going to do tomorrow. But again, it has all the rules and everything included in it. So technically you will already be able to do it, just learning it that way. Though you may just want to wait till we kind of go over it in class as well. So that'll be fine. Alrighty. Boop, boop, boop. I do have one more thing to put. A special case, which we're not going to really see until chapter 11. Though I am going to put it in your heads now, even though we're going to completely forget about it for the next, all the rest of the book, basically, is when we deal with logarithms. If you would rather not get confused, turn off your brain for the next 30 seconds or so. With logarithms, we have a special case. If a number is a logarithm, let's say you have a pH, for example, you're measuring your pool, it's going to be on canvas. I'll show you that in a second. So if you have, say, a pH of 7.26, the rule for logarithms is only numbers after the decimal are significant. So for this number, this is only 2 sig figs. All right, for special case, this is a special case for any number that is a logarithm, like a pH, that we'll find out about. That will only have 2 sig figs because we only count numbers that are after the decimal. We'll talk about that in chapter 11. Just putting it out there for now. Forget about it. Actually, I think there's one question on the homework that deals with logarithms, but after that, you can forget about it until chapter 11. So don't focus on this. I'm not going to test you on this until we get to chapter 11. So don't worry about this part. Focus on those first 4 rules. So this is technically rule number 5 or something, but it's a special case for logarithms. Okay, if we go to Canvas, let's go ahead and make this visible for you guys. Yeah, okay, let's go to Canvas. Whichever class you guys are. If you look at the homework here, I'll put it on student view so I can show you what, there we go. Okay, so as soon as you log on to Canvas, this is kind of the home page that you're gonna see. This will be the homework that you'll be able to do right away. So you'll be able to click it. It's going to have you download the PDF. It's going to have you measure some stuff. And, there's going to be some, again, it's going to have all your rules here. And you'll be able to kind of do some sig figs on these things. And yeah, so you'll have, basically you'll be able to do up to this point right here. I guess number 18 right away. We're going to cover the rest of the stuff later, but that's where you're going to find it. What you're going to do is you can either print it out and do your work on it, then take pictures of it and submit it on Canvas. So if we were to do this, where are we? Why do we have some of these? Oh, because of those are the lab sims. Okay. If you were to do this, when you're ready to submit, you will click submit here, and you're going to be able to choose any of these file types. So PDF, JPEG, or PNG. Those are the ones I allow. Typically, phones take pictures as JPEGs, though you can have little phone scanners, or you can actually scan stuff and get PDFs of it and just submit it that way. And then I'll be able to look at it and give you a score for it. I think also Canvas will, because I'm on the wrong screen. My bad. Okay, so if you click, go away. Okay, if you click this stuff, it's gonna have upcoming assignments up here that you're gonna be able to see. And so these are just lab sims, by the way. So those you can just do. Those are due this weekend. So just go through those. There is a little intro video to show you how to do these. Only worry about the ones that have due dates. I can't hide these ones from you guys right now, so just worry about ones that are coming up due. So you can always just look at this to-do list. It's going to show you what's upcoming. Later today, I will put a due date on this measurements in Sig Figs 1, so you're going to see that will show up here as well, that you can go ahead and start using. Okay? Cool. So with that, we will continue tomorrow with our Sig Fig journey. We'll start to figure out how to use Sig Figs, and that's where the tears will begin flowing. So for now, this is kind of your last day of happiness before the addition of Sig Figs comes into play. So these are technically my office hours, but you'll find that if you throw questions on Discord, I will answer them pretty much right when you ask them, if I'm on my computer. That's going to be the best way to kind of do that. However, you're going to see that I do have special kind of Twitch streams just for questions. Those are typically done on Thursdays. Those will be done the week before the exam and after the exam. So that's kind of the best time to do it. However, the second best time to ask questions would just be during our regular streams. I'm happy to answer questions then as well. Okay, so looks like we're done for today. So I'll see you all tomorrow. You can go ahead and start working on that Sig Fig worksheet, and yeah, there you go. All right, see ya.